Welcome to the Deep Dive. Today, we're tackling what has been, until pretty recently, maybe the single most frustrating limitation of powerful AI,
Oh, yeah.
their inability to actually do anything in the real world. I mean, think about it. You can have an LLM that is a complete genius. It can write poetry, it can debug your code, summarize thousands of pages.
But its knowledge is frozen in time.
Yeah.
It's completely capped by the moment it was trained.
Exactly. They are these magnificent thinkers, but they're functionally isolated.
Completely. They can't just, spontaneously check a livestock price or look up today's weather or, and this is the crucial part, interact with secure enterprise systems.
Right, like your company's CRM or your internal file structure. The moment they need to execute a real-world action or get some real-time data, they hit a wall.
They hit a wall.
Yeah.
And connecting them to those things, well, that's been the challenge.
And until the solution we're covering today came along, that challenge was a scaling nightmare. I mean, it led to these brittle, custom-coded messes that would just fall over the second a single parameter changed.
Which is why today we are diving deep into the Model Context Protocol, or MCP.
MCP.
And if you want a really quick way to grasp its importance, just think of it as the universal connection standard for AI. It's basically the USB-C of the agent world.
That's a great analogy. A single standardized interface that lets AI systems just plug and play with any external tool or data source?
Precisely. The source material had this other analogy that I thought just perfectly captured the pain point of how things used to be.
The translator one.
The translator one, yeah. It said, look, if your AI agent only speaks English, but it needs to talk to a French database, a German calendar, a Russian search engine,
Yeah.
you're stuck.
You have to custom build a translator for every single pair. That's the MXN problem they talk about.
Exactly. It's English to French, English to German, English to Russian. And then if you add a new service, say a Mandarin one, you suddenly have to build 3 more new translators.
It just doesn't scale.
It doesn't scale for people, and it definitely doesn't scale for complex AI systems. So MCP becomes that single universal translator. The English-speaking agent talks to the translator, and the translator handles everyone else.
Okay, so our mission for this deep dive is to really get under the hood of how this protocol works architecturally, how it slashes that integration complexity, and this is the most important part for you, the person actually building or using these things, how it makes sure the AI can use powerful tools without, causing total chaos.
Right.
So let's start by really unpacking the severity of that M by N nightmare. What did the world look like before MCP? What was the real fallout of that patchwork of one-off solutions?
Well, the problem was really twofold. You had complexity and you had fragility.
They sort of feed into each other, I imagine.
They do. Imagine a pretty standard mid-sized operation. You might have, let's say, 5 different AI applications running.
Okay, like one for marketing copy, one for internal code review, maybe a few customer service bots.
Something like that. So that's your M. M equals 5. Now, they all need to interact with 5 core enterprise tools.
Right.
GitHub, Slack, the company database, the calendar, and the local file system.
So N equals 5.
Right. So you needed 5 times 5 or 25 separate custom-built integration modules.
25 modules, just to get 5 models talking to 5 tools.
25. And every time you wanted to swap out a model or maybe introduce a new service like Teams, you had to write 5 brand new bespoke integration paths from scratch.
What a massive drag on developer time.
Oh, it was a huge inhibitor to enterprise adoption. It was rigid, it was slow, expensive, and frankly, it introduced a lot of security vulnerabilities because every connection was this unique, hard-coded thing that had to be maintained separately.
So the core value proposition of MCP is just simplifying that equation. How does the standard bring M times N down to M plus N?
It just creates a standardized API boundary right in the middle. So instead of the AI models needing to learn how to talk to every single tool, they only need to learn one language, MCP. So using our old example, the 5 AI applications, they now only implement the MCP client side once. So that's M equals 5 implementations.
Yeah.
And the 5 tools, your GitHub, your Slack, your database, they each implement the MCP server side once. So that's N equals 5.
5 plus 5. 10 total connections needed, not 25.
Correct. And the real magic is the moment you want to introduce a 6th tool, you only write one new piece of code.
The server implementation for that tool.
Exactly. And suddenly, all 5 of your existing AI models can use it instantly. You don't have to touch their original code at all. This is the fundamental shift you need for these systems to scale into a real ecosystem.
That structural change makes total sense. To really appreciate how elegant it is, though, we need to look at the architecture. It's a client-server model, but it's tailored specifically for AI agents. So let's break down the three core roles: the host, the client, and the server.
Okay, so the host is the highest level. It's the part you, the user, actually interact with.
So the application itself.
The application itself. Picture an AI-enhanced IDE, or maybe a dedicated app like the Claude desktop client. That's the host.
And the host is the decision maker for the user experience, right? It's capturing your input, it's managing the conversation history, and crucially, it decides when it needs to reach out for external help.
Exactly right. And then living inside that host is the second role, the MCP client.
Okay.
Think of the client as the low-level adapter, the messenger. If the host decides, okay, I need to check the file system to answer this, the client's job is purely technical. It knows how to speak the model context protocol, and it handles the mechanics of opening the connection and structuring the request exactly how the server expects it.
So the host decides the strategy, what to do, and the client handles the tactical execution, how to speak the language.
Perfect. And that brings us to the third piece, the MCP server. This is the external program. It could be running on your local machine, or it could be out in the cloud somewhere. The server's job is to wrap the actual capability, the tool, the data, whatever it is, and advertise what it can do in that standard MCP format.
So it's basically shouting, hey, over here, I've got a tool called Create Calendar Event, and it takes these two specific parameters.
That's it. So you have this really clear separation of concerns. The host manages you and the model, and the client-server pair manages the standardized communication with the outside world.
Okay, so once that communication link is established, what's actually being shared? This brings us to the three core capabilities the MCP server provides: tools, resources, and prompts.
And this is so important for security and reliability. We really need to define these three categories clearly because they represent very different levels of risk and control. Let's start with tools.
Tools are the heavy hitters, right? These are the executable actions. They have side effects. They change things in the real world.
That's right. We're talking about booking a flight, sending an email, writing a file to cloud storage, updating a record in a database. These are powerful actions.
And crucially, these are model controlled.
Yes. The LMM itself decides, based on your intent, that calling the book flight tool is the necessary next step in the process.
Which sounds powerful, but also a little scary, which is why there's a security gate built right into the protocol.
There has to be. The MCP structure often requires explicit user approval for these model-controlled tools. The host application, your IDE or your chat client, can intercept the LLM's decision and pop up a little confirmation box.
The AI wants to run SendMail. Do you approve?
Exactly. This ensures that a human is always in the loop and retains the final say over any action that actually changes the state of the world. It's a critical check.
Yeah, a good example we saw was a simple Python function like getWeatherLocation that's just wrapped with an @mcp.tool decorator on the server side. The LLM calls it, the server runs it, and it just returns a clean, structured JSON object.
Temperature, conditions, humidity. Easy for the LLM to understand and weave into its response.
Okay, now contrast that with the second category, resources.
Right. Resources are fundamentally passive. They are read-only data sources. You use them for information lookup. They have zero side effects. They can't modify anything.
So they're just reference material. And if tools are model controlled, who controls the resources?
This is a key difference for security. Resources are typically application or host controlled. The host application decides when it's appropriate to go fetch some context.
So if I ask the AI, hey, summarize the progress on the Q3 project, the host itself is what goes and retrieves the relevant parts of the knowledge base.
Exactly. It retrieves that context via an MCP resource call and then feeds it to the model before it generates a response. The host controls the gateway to sensitive data.
This is huge. It means you can get really powerful information retrieval without just handing the LLM the keys to your entire file system.
Precisely. You see it used for fetching sections of a company handbook, querying a knowledge base, or even just reading a local file via a standard URI format like file.path. They're much less dangerous than tools, but all the privacy and access is still managed by the host.
Okay, that leaves the third one, prompts. Now, we all know what prompts are, but why on earth would they be managed by a server?
It's a great question. In the MCP context, prompts aren't just simple instructions. They're predefined instruction templates or entire conversation flows. Think of really complex system roles or multi-turn workflows.
Okay, so they're usually user-controlled, like I pick a template, or developer-controlled, where a specific behavior is mandated.
Right. And the reason you put it on a server is all about decoupling maintenance. Instead of your host application having a massive hard-coded system prompt for, say, a meticulous code reviewer persona.
The host just pings the server and says, hey, give me the latest version of the meticulous code reviewer prompt.
You've got it. So if a developer realizes that prompt needs a tweak, maybe you need to add a step to check for dependency versions, they just update the prompt on the server. Instantly, every single client application gets the improved workflow.
Without a single client-side code change or redeployment.
Zero. It ensures consistency and makes updating complex behaviors trivial.
That level of standardization is great for stability. But now let's get into where MCP really leaves the old ways behind, its dynamic nature. We've all seen traditional APIs break. How does MCP fix that fundamental fragility?
Traditional APIs operate on these static contracts, like a paper menu at a restaurant. If that weather API expects location and date, and then tomorrow the developer adds a new required parameter, like unit for Celsius or Fahrenheit,
Every single client application built on the old menu instantly breaks.
it breaks. The LLM has no idea what to do because the instruction set it was given is now wrong. And that requires a massive manual effort to refactor, test, and redeploy everything.
So how does MCP avoid this?
It uses dynamic capability discovery. It's the difference between that static paper menu and a constantly updated digital menu board.
Right.
When an MCP client connects to a server, the very first thing it does is an information handshake. It asks a question.
What's the question?
Tell me your current capabilities and your requirements. It's an inquiry, not a command based on old assumptions.
Ah,
So if that server adds the required unit parameter, it just dynamically updates its own description of the weather tool. The next time the client connects, the LLM agent sees the new requirement in the description and just automatically adjusts its next call to include it.
and the client application code is never touched.
Remains completely untouched.
Oh.
That adaptability is absolutely critical for any kind of complex, evolving agent system. It lets the LLM become a much more resilient consumer of tools. It stops guessing and starts asking.
And this is why it's so much better than just stuffing a list of old-school function calls into a model. It fixes the MXN problem and it handles change gracefully.
It creates an ecosystem that can actually grow and evolve without constant human intervention. But that rapid growth, it introduces a new problem. Scale.
Right. What happens when your AI agent has access to hundreds of these dynamically discovered tools across dozens of servers? The sheer volume can cause it to fail.
The sources were very clear about this. The LLM just gets overwhelmed. You see three main failure modes.
What are they?
First, you get tool name hallucinations, where the model just invents a tool that sounds plausible but doesn't exist. Second, you get real confusion when it has to choose between tools that have similar functions.
And I'm guessing the third is just bad decisions.
Degraded decision quality, yeah. The cognitive load of navigating that huge tool dictionary is just too high, and it starts making inconsistent choices.
So MCP makes it super easy to connect all these tools, but then how does it help the AI manage them all without getting confused?
That is where the server manager comes in. This is a built-in orchestrator. It's often part of simplified frameworks like MCP use, which is an open source library that lets you build these agents in, like 6 lines of code.
Okay, so the server manager's job is to act as an intelligent gatekeeper.
That's a perfect way to put it. It keeps the LLM's workspace clean. It makes sure the agent's active toolset stays narrow and context-driven.
So it's not showing the LLM all 200 available tools at once.
Never. The server manager dynamically loads tools only when they are semantically appropriate for the current task. It can do a semantic search across everything available, find the exact right server and capability you need, and then it surfaces only that tiny, relevant set to the LLM.
And enabling this is just a single flag, right? Something like use server manager.
Sure.
Too.
That's it. But the impact is huge. It virtually eliminates that tool overload problem and ensures stable decision-making by just radically reducing the number of options the LLM has to consider at any one time.
And this management system seems to be what enables the really interesting two-way communication to happen securely. We've talked about what the server provides, tools, resources, and prompts. But you're saying the client also exposes capabilities back to the server.
Exactly. The communication is fully bidirectional. There are 3 client-side primitives that the server can call.
Okay, let's unpack those. What's the first one? Sampling.
Sampling is the ability for a server to ask the client's LLM to generate a completion for it. So imagine a travel booking server. It's successfully run a search, and it has a list of, say, 10 flight options.
Okay.
The server itself isn't smart enough to pick the best one. It's just a tool. So it can use sampling to send that list back to the client's model and say, hey, analyze these options based on the user's preference for minimal layovers and pick the best one for me.
So the server offloads the high-level judgment call back to the LLM. That's clever.
It is. The LLM returns the structured choice, and the server just proceeds with the booking. It keeps the logic where it belongs.
Okay, what's the second primitive? Roots.
Roots directly addresses the security of letting external tools access your local files. It allows the client to define very specific, secure directories, sandboxes really,
Yeah.
that an external server is allowed to access.
So a code review server could be given access to just the project folder, and it would be physically blocked from browsing my personal documents.
Exactly. It's granular permission management right at the file system level.
And that brings us to the third one, which this one seems to open up some really futuristic possibilities. Elicitations.
Elicitations are wild. This allows the external server to pause the entire workflow and send a structured request back through the client to ask you, the user, for clarification or for some missing information.
Wait, so the tool can prompt the user. The tool can effectively start driving the conversation.
Absolutely. Think about that flight booking example. The server runs the search flights tool, but now it needs the user's passport number to finalize the booking. The AI model doesn't have that and shouldn't store it.
Right.
So the server uses an elicitation to basically inject a structured input field into the host application, pausing the whole transaction until you, the user, provide the required information.
That is a true dynamic negotiation. So we've really moved beyond just these brittle, hard-coded connections or simple prompt chains. This is a robust, standardized, and secure ecosystem.
It fixes the scaling problem. It allows the models to become powerful decision makers. But it keeps the critical security and control firmly in the hands of the user and the host application.
This feels foundational, like you can't build reliable, scalable AI agents that do complex real-world tasks without something like this underneath.
I think that's right. The standardization is what lets the whole ecosystem accelerate without just collapsing under its own complexity.
Okay, so as we wrap up, what's the final provocative thought you want to leave our listeners with? Something for them to chew on.
We talked about the server manager turning the agent into a kind of workflow manager, but I want you to really consider the power of elicitations. Think about what it means when a remote tool, running on a server maybe hundreds of miles away, can pause an entire complex workflow, a task involving dozens of steps, and send a structured request back through the client to ask you for clarification before automatically resuming without missing a beat.
That's a different level of interaction.
Yeah. It's a different paradigm. That level of dynamic, multi-directional negotiation, where the external capability is actually guiding both the user and the agent in real time, that fundamentally redefines what we think of as sophisticated AI interaction. That's the future that MCP really enables.